This is AP Calculus AB. We're looking at implicit differentiation. Video 1 of this tried to explain to you when we would use implicit differentiation. And in this second video, we're going to discuss how you would use implicit differentiation. Video 1, we said we would use implicit
differentiation when we either didn't have the equation solved for y and couldn't or didn't want to. So let's check out this first example. How do we use implicit differentiation? Well, implicit differentiation relies on the chain rule, but it looks a little bit different than how we would typically look at the chain rule. Let's look at this first example and see if we can make sense of this. For the equation, x squared plus y equals 25, determine the derivative of y with respect to x at each of these points. In order to do that, we need to first figure out what dy over dx is. So I'm going to take this function, x squared plus y equals 25. I'm going to find the derivative. And the important part here is it says find the derivative with respect to x.
Treating this differently than we've done explicit functions. And why would we do it differently? Y is not by itself. An implicit function is when y is not by itself, and here it's not by itself. We are going to treat each of these functions as if there's an inside and an outside. So for example, this is an x, this is the inside, outside function squared. For the y is on the inside, and the 2 squared is on the outside. So we're going to use the chain rule for each of these. So what's the derivative of x? Well, I'm sorry, the outside. What's the derivative of x squared? We put the 2 in front. Inside stays the same. Subtract 1 from the exponent. 2 minus 1 is 1. Then we multiply this by the derivative of the inside. The inside is x, so we would say dx over dx. Just work with me here. You might be thinking, we haven't done that all year. Why are we doing that now? We could have been doing this all year, and we haven't done it now. So let's continue, and I'll come back and talk about this more. So this is y squared. If we use the chain rule, derivative of the outside, we put the 2 in front. Subtract 1 from the exponent. The inside stays the same. Subtract 1 from the exponent. 2 minus 1 is 1. Then we multiply it by the derivative of the inside. Since we don't know what y is, we say dy over dx. Then over here, derivative of 25 is 0. Technically, if you then wanted to say times the derivative of 25 with respect to x, you could. I'm going to highlight a few things here that aren't necessarily needed, but if you want to include these things in these problems, you can. Neither of these things in blue are needed. Here's why. The derivative of x with respect to x. Remember what derivative means. It means how is x changing as x is changing. Well, they're going to have a one-to-one relationship. So this is the same thing as just 2x times 1. How is y changing with respect to x? We don't have any idea. So that has to stay there. And here on the right, how is 25 changing with respect to x? It doesn't really matter because we're multiplying it by 0 anyhow.
To sum this up, what just happened, because we don't have to necessarily do this entire step. If when you take the derivative, if it's the correct variable, if it's the same variable, it's just business as usual. If you take the derivative and it's with respect to a different variable that's in your term, not business as usual. You have to also use the chain rule and take the derivative of the inside with respect to x. Now we were supposed to determine the slope dy over dx at each of these points, so let's get dy over dx by itself. I'm going to subtract 2x from both sides of the equation. That would give me 2y times dy over dx equals a negative 2x. And if I divide both sides by 2y, I get dy over dx is negative 2x over 2y. And we could cancel a 2 from the top and the bottom. And we get the derivative is negative x over y. Now, before I continue, let me just take a trip back to our first page here. This was the first function we looked at on the first video for this. So we took this function, and we got y by itself. I just want to show you that this derivative is not different. It looks different than what we're used to, but it wouldn't actually be different had we gotten y by itself. If we replace y with this, then this derivative, you don't need to write this down, would be dy over dx is negative x over plus or minus the square root of this monster. Had we got y by itself originally and found this derivative explicitly, we would have got this for the answer. Notice how much simpler this is. Y is this. These are the same thing. Let me get rid of this, and let me get rid of this. Determine dy over dx, did it, and determine that at each of these points. So to show this work properly, let me bring these points down here. This is the proper notation. Dy over dx evaluated at, this vertical bar means evaluated at, 0 and 5. We're going to put 5 in for the y value, we're going to put 0 in for the x value. It will be negative 0 over 5, which is 0. Before we do these other points, let's just examine this looking at the graph. We weren't asked to graph this, but I just want to do it to make sure you understand. This, once again, is a circle. Its center is at the origin, and its radius is 5. Hopefully you remember that from geometry and from pre-calculus. So this is the circle. Here's the center at 0, 0, and has a radius of 5. If I take this ordered pair 0, 5, which is right here, we are saying that the slope of the tangent line would be 0, which means this would be a horizontal line. And I think we would agree that that makes sense looking at this picture. Well, what's the slope of this curve at the ordered pair 3, negative 4? Showing our work correctly, we would say dy over dx, evaluated at 3, negative 4. We're using this slope here, negative x over y. This is x, this is y. So it's negative 3 over negative 4, which is 3/4. My apologies. So we're putting x in here to the top, putting this in, y into the bottom. So the slope would be 3/4. So from this point, I would go up 3, 1, 2, 3, and to the right 4, 1, 2, 3, 4, put a dot there. Similarly, if I went down 3 and to the left 4, that would be here. You can see how that would be tangent. This is at the ordered pair negative 3, 4. Slope's 3/4. So far, so good. And then finally, we're supposed to find the slope at negative 5, 0. So that's dy over dx, evaluated at negative 5, 0. We have a negative x on the top and a y on the bottom. So it would be a negative 5. It would be 5 over 0, which is undefined. What kind of lines have an undefined slope? Vertical lines do. Just like slopes that have 0 is a horizontal. So at the ordered pair, negative 5, 0, which is right here, we would have a vertical tangent line because the slope's undefined. All right, let's look at 2 more examples of implicit differentiation. Now, if you look at this, the directions don't tell us we have to use implicit. So if it's easier for you to get y by itself at the beginning and then do it explicitly, by all means, go for it. That's not going to happen for this one. This is impossible for me to get y by itself. People better than me, better men than me, better women than me could do it. I don't know how to do it. So we're going to do this implicitly. You do implicit when y is not by itself. And we're going to use the chain rule. Before we get into this, let's be sure that we know this is a product. This right here is just going to be the power rule. This is going to be the power rule with a little chain action. So I'm going to continue to write the dx over dx, the dy over dx, even though sometimes when it's not necessary. Okay, so doing this implicitly, we're going to treat every one of these variables like it's its own function. So the outside function here is going to be 3x, pardon me, it's 3 something to the 4th. So the derivative of that power rule, we're going to have 12x, subtract 1 from the exponent, that's 3, times the derivative of x with respect to x. Now that dx over dx is not necessary. This next one is a product, and I'm subtracting this product. So I'm going to put this in a grouping symbol. Take the derivative of the first. Actually, I'm not going to write this for this problem. If you need to write it to make yourself feel better about this, go ahead. But basically, the only time that we need to write the derivative of the inside is if the variable we're using is different from the denominator. So this denominator, the dx with respect to x is an x. So product rule. Derivative of the first, x, is a 1, times the second. Notice, nothing special happens here because we're just saying the second function. The first function is the correct variable, plus. I write down the first function, x, times the derivative of the second. The derivative of y is 1. It's the wrong variable because it's supposed to be with respect to x, but this is a y. So then I say dy over dx. That is implicit differentiation. It's essentially the chain rule because y is some elaborate function and we don't know what it is. Plus, the derivative of y cubed is 3y squared. It's the wrong variable, so we put dy over dx. And this is equal to, the derivative of 12 is 0. That is implicit differentiation, what just happened. We are supposed to get dy over dx by itself, and that cannot happen until we can clean some stuff up here. Let's distribute this minus. And I am emphasizing this being distributed, so I'm going to draw this. We're going to get 12x cubed minus y plus x times dy over dx plus 3y squared times dy over dx equals 0. Now you'll notice that there are 2 terms here that have dy over dx in it. You can't add those together, they're not like terms. There are 2 terms here that don't have dy over dx in them. I'm going to move these to the right side of the equation by subtracting a 12x cubed from both sides and adding a y to both sides. What does that do for me? Well, that gives me the y on the right and a minus 12x cubed on the left. I can take these 2 terms that are left on the left, and I can factor out a GCF, which is a dy over dx, leaving me with an x plus 3y squared. Ah, I messed up. Doggone it. The emphasis, I didn't do this on purpose either. The emphasis here, distribute the minus. I said it, I didn't do it. Shame on me, my entire family. Minus, which means this right here. Not that right there. So it'd be a negative x. Let me just make sure I did that correct. This is the nice thing about showing your work. When you show your work and you make a mistake, you can work backwards and see what your mistake was. So I distribute the minus. So it's a negative y minus x dy over dx. I move this stuff to the right. It's going to change both their signs. So then I have a negative x and a plus 3y squared. I factored the GCF of dy over dx out to the front. So it looks good now. To get dy over dx by itself, I'm going to divide both sides by this monstrosity. And I prefer my leading term to be positive. So I'm just going to choose to rewrite when I divide both sides by this as 3y squared minus x. You would not have to do that. Find dy over dx, we found the derivative with respect to x. So if we were supposed to evaluate this, we'd have to know an x and a y value to be able to do that. Let's check out number 2. Same directions. Find dy over dx, which means we have to take the derivative of each term with respect to x. So this is the wrong variable. So when we take the derivative of cosine, it's negative sine. Inside function stays the same. Then we multiply that by the derivative of the inside. And since we don't know what y is not just y, it's some function, we say we don't know what the derivative is, we're going to write dy over dx. And if you don't care for the explanation, then always do this. Anytime you take the derivative and it's the wrong variable, that's an x, this is a y, always put d, whatever variable you have, over whatever variable it's supposed to be. The derivative of 3x is 3. We need to add anything to that. Technically, if you want to put dx over dx, you could. That derivative is 1, so we don't need to. Add to that, derivative of 3y is 3. Is it the correct variable? It is not. So we say times dy over dx. Now, we're supposed to get dy over dx by itself. I'm going to subtract this from both sides. And that's going to give me a negative 3 times dy over dx minus sine of y dy over dx equals 3. I just subtracted this from both sides. Now I can factor out this GCF of dy over dx, leaving me with negative 3 minus 3y, not 3y, negative 3 minus sine of y. Tell you what, I don't like double parentheses. I'm just going to make this brackets. You don't have to do that if it doesn't bother you. To get dy over dx by itself, I divide both sides by this little fella. This little light of mine, I'm going to let it shine. And we got dy over dx by itself. So we just looked at 3 different examples of how to use implicit differentiation. To sum up, if you take the derivative of a term, and it's not the same variable as the denominator of what you're trying to take the derivative of, then you have to put the dy over dx with it, or the dr over dx, or dt over dx. I had a student once that said, it's like sprinkles. And I said, Brock, what are you talking about? He said, well, if you have a function, like, let's say x squared plus y squared plus z squared equals 3, and you were supposed to take the derivative of this whole thing with respect to x. He said, if it's the same variable, you just do it the same, and I agree. If it's a different variable, so the derivative of y, with respect to x, you put some sprinkles on it. He called this sprinkles. Sprinkles like on ice cream. Derivative of z squared is 2z. It's the wrong variable, so you put some sprinkles on it. So when this student explained this to the class, everyone thought he was nuts. And by the end of the day, everyone in my class called this sprinkles. So, whatever. That concludes the second video. The third video is going to be some examples of some AP test-like questions.